Class, welcome back to CSC 143. We are now in week 9 of our 10-week course. This week we're going to be reviewing binary trees. Just as a quick reminder, this course CSC 143 is the second of 2 introductory courses based on the University of Washington's curriculum. And there's information here on where you can get the book and get it online. And this course is currently being offered at the South Seattle College, and you're welcome to come and join us in person if you'd like. So we've done all of these weeks so far, week 1 through 8, and now we're looking at binary trees. This video is going to be covering binary tree basics and probably binary tree reversals. We'll see how far we get. As always, I'm using the slides of my dear friend of over 30 years, Dr. Amelia Gahn. Thank you, Amelia. And her statement this week is keep bifurcating, which means keep on splitting up into 2 and 2 and 2. So binary trees. Before I start launching into what a binary tree is, I just want to state how unusual this week is. Normally we're learning about structures that are available in Java, such as a map or a set, with implementations that you can just go and say new hash map, new tree map. And this week that's not the case. We are learning about an abstract concept of binary trees for which there is no simple straightforward Java implementation. We're actually going to create our own implementation. But as you may have noticed from that last sentence, we do have tree maps and tree sets. So you already know a few things about trees. So as we go through this week, just remember that it's going to be different than in past weeks. We're not looking at a particular implementation. We're actually looking at a concept. So a binary tree uses links. We've already learned about linked lists. But it's no longer one-dimensional, whereas a linked list is just one-dimensional, a line. A binary tree is, as this picture shows, it looks like a tree structure, except, of course, all our trees are the other way around. It's upside down. You start from a single node that we call the root, and the root is the only node that has no parent. And you'll see that comes into special play in our implementation. And each node can have up to 2 child nodes. So here we've got a root, we've got branch nodes. Our terminology in the real world for branches is a little bit different than the computer terminology. Branch, really, it would be more accurate to call it a branching node. So it's got branches on it, okay? Normally, if you just break off a stick from a tree, you call it a branch, whether it's got other sub-branches on it or not. But in computer science, we call these branch nodes only if they have branches on them. And then finally, we have leaf nodes, where, just like in a real tree, it's the end. There's nothing further than that. Lastly, one bit of terminology is the height of a binary tree. This is a little bit confusing because, you know, just intuitively looking at the height of this, you would say the height is 4, but actually, technically, the height is defined by the number of edges. So that's number from top to bottom, so that's 1, 2, 3. So the height of this tree is actually 3, and the height of a root, which has no children, is 0. It's a little bit strange, but hey, it's computer science, so I guess we got to start with 0. So a binary tree can either be an empty tree, which is not the same as just having this root node. An empty tree you can't even draw because it literally doesn't exist. And why is that useful? You'll see when we write our recursion, you will see that the base case is going to be an empty tree. So you literally have nothing. Okay. So an empty tree, the base case is not a root node, but it is rather nothing. And a root node can then have a left and a right subtree, and then the left and right can, of course, have their own subtrees. This is a recursive definition, and the common problem in students looking at this chapter is they get confused about always wanting to do the work when they look at the subtrees rather than doing the work in the base case. And you'll see that the work is usually actually done in the base case to a lot of extent. So here's another picture. The simplest case, base case, is the empty tree, which is not drawn here. And the recursive case, you have a root, a left, and a right. So again, what I was saying earlier, there is no Java tree class. there is a tree map and a tree set, but there is no simple tree class. And the reason as to why that is has been lost to history. But we instead have to create our own tree class. So the simple data structure that the book comes up with is called int tree node. And that's a simple class that has a binary tree using integers. At the end of the chapter, we actually show you how you can create a tree structure that is parameterized so that it doesn't have to be int all the time. It could be a string, it could be your own data structure, anything like that. So this data structure contains a data, so that's the integer that's going to be stored in a particular node. And then it can have a left and a right subnode. Those could be null. And as an example here is a constructor. It takes a piece of data, so that maybe that's the value 5, and then it creates a default of null for both the left and right children. Or there's another constructor here where it takes the left and right nodes, so you can give it not only that data like 5, but also give it a subtree on the left and the right. Now what we just looked at is a node in the binary tree, but you actually still need a separate class that is the actual root of the tree. So here's binary int tree. See, before we were looking at int tree node. So this is binary int tree, and it has a int tree node. So it contains it, and the only thing that this can do is give you the root. The next subject is from chapter 17.2, tree traversals. So the question is, how do you look at this data structure? How do you traverse it? So the best way to do this is recursively, because these structures are inherently recursive. And there are 3 options to do it. I'm going to skip past this slide and show you. Here, there's 3 nodes here. You can do it what's called pre-order, where you go in the order of the parent first, and then the children. You can do it in order, which is that you do it the left side, and then the parent, and then the right side. Or post order, which is you do the left side, right side, and then the parent. And let me show you a simple way to do these. Here, this is gonna, unfortunately these slides don't show it, but the book shows an excellent drawing of this. It's called the sailboat methodology. So you imagine there's little sailboats sailing around these islands per se, and depending on which order you want, you look at the nodes and report them in a certain fashion. So for pre-order, what you do is that you imagine you're looking out this boat, and whenever you see a node and such that the boat is on the left side of a node, here and here, you're going to report it. So take a look at this example here with the numbers here. We're going to go pre-order 2, 0, 7, 6. Then we sail around here, we come to 5. Then we have to sail all the way around to here, and then we are on the left side of this 3. But notice we didn't do 2 yet. Or sorry, we already did 2. So we're going to do 3, and then 1, 8, 9, and 4. In order is the same pattern, but now we're only going to report nodes when we're looking underneath them. Okay, so we're not going to report 2. We're not going to report 0 or 7. We're only going to report a node when we're underneath it. So that's 6. Now we come up here and we report 7. Then we are under 5. Then we're going to come back and we will see we're underneath 0. Now we're underneath 2. And now we're going to skip over 3, 1. We're going to come to 8. And then 1. And then 3. And then 9. And then 4. So notice that when you try to come underneath this node here, you can't really come underneath because you're being blocked. Okay, so don't think, oh well, I can squeeze under here. That's not the way it works. Okay, don't try to squeeze in. If there's a child then on the left, then you can't get to it. All right, finally, post order. So now we're only going to do it when we end up on the right side of something. So we're going to go down here. We'll start reporting 6, but not 7 because we can't get to the right side yet. 5, 7, 0. We can't get to the right side of 2 yet. Can't get, nope. 8, 1, nope. Go all the way down here, 4, 9, 3, 2. So that's the sailboat methodology for how you figure out the pre-order, in-order, and post-order. I would suggest you take a look at my videos for some of the exercises and self-checks, because I also give some motivation for why does pre-order, in-order, and post-order matter. The reason it matters is because given a single binary tree, there are multiple ways to interpret it. In this example here, you're getting these numbers in a different format, but that's pretty meaningless to you and I. But I show you that if you interpret this tree as actually being an expression, you can evaluate the expression in different forms. So take a look at that in my other videos. So we want to be able to print out the tree. So here's some code to be able to print out the tree. And as we talked about, you've got this overall root. In this case, you assume that overall root is it's a class variable because it's not passed in as a parameter. So we take the overall root and then we call an helper routine which takes a root. We need this helper routine because as we recursively call, we need something that's going to actually take a node, an entry node. So we always have to have helpers in these kinds of functions. So what is this thing going to do? If the root's not null, then it's going to print the left. Then it's going to print the root, the parent root itself, and then the right. And we can do the same thing for the pre-order by printing the node before it's left and right, or we can do the post-order by printing the node after the left and right. So recursive code is very compact. It's confusing because it's so compact. A lot of students are left wondering, how does that work? What's going on here? A lot of students are going to want to manually do it by, iteratively going down the left and the right and whatnot, but it's so much easier if you do it recursively. The last topic in 17.2 is the code to actually print out your binary tree. Now, this jumps the gun a little bit early because 17.3 covers a lot of code on how to traverse trees, and this is maybe more complex, so you might want to watch 17.3 before you watch this one. But let's press on. So they're going to print out the tree what they call sideways. And so you can see this is how they want it to be printed out. And Amelia's rotated it here for you to show you how the tree structure works. Unfortunately, the numbers are actually rotated as well, so it's a little bit hard to read. But you can see what happens is that on each line, there's only one node. Even though it kind of looks like it's printing out a tree, it's a very clever way of printing it because each line is only one node. That makes it easy. And also, let's take a look at how it works. Okay, so it's printing out 85. That's the rightmost child. And so we want code that comes all the way down the right, the right, the right, the right, the right, and only when we're done getting to the very end do we actually print. Then we come back and we print the center. And then we come back, we print the center, and then we come back, we print the left. So we do right, center, and then left. And that's actually true of the entire tree. We're always doing the right, and then center, and then left. And we also are able to localize our printing so that we don't have to jump all over the tree. So for example, even though it looks like 3 and 85 are at the same level, we don't have to print them at the same time, right? We actually print 85 right at the beginning, and 3 is second to last. That's because it allows us to always work our way up the tree and not have to jump around. If we were to try to print it with 7 at the top, and then 6 and 8 and the next line, we would have to jump all over the tree. So this is a much easier way of doing it. So what we want is code that recurses down the tree, prints out the right child first, then the center, then the left. Okay, so remember that. Right, center, left. Let's see what the code actually looks like. So we always have a helper function in the trees because we need to grab the overall root. If we were to try to do it with this just one function, and we were always trying to recurse, well, we couldn't start at the overall root and then pass it in. So we've had to start with a helper function. And then this code looks a little bit complex, but I want you to ignore what's happening in these 3 lines here. If you ignore that, you see that we print the right, the center, the data, okay, and then the left. That's all it's doing, right, center, and left. It gets a little complex only because we have to include the level, and the level then calculates this indent by just having a simple for loop to indent it over the appropriate number of levels. But other than that, there's just only like 4 lines of code. So it's really a very simple process to print that out. That's the end of chapter 17.2, Tree Traversals. Be sure to come back and watch my 17.3, where I'm going to show you in code how you do a lot of common tree operations. So if you found this video useful and you liked it, then please like and subscribe. That helps other people find my videos.